Alrighty, it's 8, so let's go ahead and get started. I wanted to make you all aware that I've uploaded some files in a folder in the introduction section called Resources. So this folder contains 4 files, one for the on semiconductor C5 process, which is what we designed to last year. So that is a relatively long channel process with a scaling factor of 300 nanometers. Then we have the CMOS EDU models. Those are the ones that are used in the textbook. It's both the short channel and long channel. So the long channel has a scaling factor of 1 micron, and the short channel has a scaling factor of 25 nanometers. Lastly, we have the Taiwan Semiconductor Manufacturing Company models for their 180 nanometer process node with a scaling factor of roughly 100 nanometers. We are going to be working examples that will use all 3 of these different models, and so that's why I've included them. Also, a very important document is the Scalable CMOS Design Rules, which is a document that's put out by MOSIS. MOSIS is an academic entity that's associated with the University of California at Berkeley, I believe. They are not a foundry, but they are kind of an intermediate with most of the foundries in the world. And so their set of design rules is adapted internationally, and it's used to try to make sure that you get the most usable devices out of a process run. And so we're going to be referring to this document extraordinarily frequently. So there's some introduction stuff, then there's the names for how the different process nodes are named. So for instance, we're going to be doing probably the on-semi SCNME submicron. And so what that means is it's scalable CMOS rules with 3 metals, and the E, I'm not sure why they use an E, says electrode, but it's a second polysilicon layer that's going to allow us to form capacitors. So that's what we're going to be designing to. And today we're going to be talking about wells, so it's important that we pull up, excuse me, the CMOS design rules associated with wells. And because we're in a submicron process node, we're going to be using the rightmost column. Alrighty, so let me switch over to my notepad here, if I can find it. There we go. And minimize this guy. All right. So the first thing we're going to talk about, and this is going to be fairly brief, is a substrate. Change the thickness. All righty. So hopefully you all know by now that CMOS circuits are fabricated already. On a silicon wafer. So we'll be looking at 2 particular views of portions of our wafer throughout this class. The first of which will look something like this. So here is our CMOS die. And to give you an idea, This is our x-axis. That does not remotely look like an X. Here's our y-axis. And then directed out of the page is our z-axis. And this is a top-down. We're also going to be fairly regularly looking at what would be called a cross-sectional view. Where the top line represents top surface of our wafer. The bottom line represents the bottom surface of our wafer. And our coordinate system in this case, X, Z, and the y-axis is the one directed out of the page. So we're going to be starting looking at some pictures like this pretty shortly. Alrighty. These silicon wafers are doped because silicon by itself, excuse me, isn't conductive enough to be able to operate effectively. So we can say that wafers may be doped by either a diffusion process or ion implantation processes. With donor atoms like phosphorus and arsenic to make N-type wafers. Or with acceptor atoms like boron and gallium to make P-type wafers. And hopefully everybody knows this, but an N-type wafer has an excess of free electrons, and a P-type wafer has an excess of free holes that allow for charge conduction. So we can actually create NMOS and PMOS transistors on both N-type and P-type wafers. So give me a moment to draw you guys a couple little pictures here. So this is again our bottom surface. Then we're going to have a very thin oxide layer. Here we have a P+ implant and another P+ implant, and above it draw, there we go, we have, polysilicon gate. And so this, if our substrate in this case happens to be an N substrate, this is how we would create this is how we would create a Pnp transistor. To create an NPN transistor, what we have to do is we create a P well inside. So over here, we could create a P well. And then we could have an N implant, another N implant, and here is our polysilicon gate. And so what the P-well does is it serves as a local substrate for that NPN transistor. So this is a P-well process, cross-sectional view. And now here, let's say that we have a P substrate. We could fabricate, oh, sorry, let me draw my insulation layer, or oxide layer. So in a P substrate, we can fabricate an NPN transistor directly. And we will need to use a well to fabricate a PNP transistor. And so this would be an example of an N-well process, cross-sectional view. Alrighty, so the P-type wafers are the ones that are most commonly used in industry. This partially explains why the overwhelming majority of textbooks that teach you about particularly analog electronics that utilize CMOS technology typically tend to focus all of their derivations on the NPN transistors and how they behave. And it's because they're the more common transistor model. Right, so that's why we're using P-type substrates. So as I said a moment ago, in a P-type substrate, NMOS transistors are fabricated directly. In the substrate. And PMOS transistors are fabricated in an N well. So this N well is created by a process called counter doping or compensation doping. Do any of you guys remember what compensation doping is from, say, your ELEN 334 class?
Can't say I do.
Alrighty. Substrate, dang it, stop. All right. So compensation doping. So let's say that we have a P-type substrate and we want to create a Pnp transistor in it. So that means that we're going to have to fabricate an N well. All right, so in order to put an N-type anything in a P-type substrate, that means that we need to exceed the doping level of the substrate itself, right? So for example, let's say that we have a doping level of 1 part per million acceptor atoms in our substrate. All right. So let me write this down. So there is roughly, I think it's 5 times 10 to the 22 silicon atoms per cubic centimeter. I believe that's, don't quote me on that, but it's somewhere pretty close to that. It's between 1 times 10 to the 22 and 1 times 10 to the 23, if my memory serves me correctly. So this is a pretty good middle ground. So 1 part per million doping means that the number of acceptor atoms, or the concentration of acceptor atoms in this case, would be roughly 5 times 10 to the 16. Let's see, acceptor, so let's call this boron atoms per cubic centimeter. So in order to create an N well in a particular region, we would need to put in, let's say, 5 times 10 to the 16 phosphorus atoms per cubic centimeter to make that region electrically neutral, right? Because if we put in the same number of acceptor atoms and the same number of donor atoms, all of the holes created by the acceptor atoms will recombine with all of the electrons that were put in with the donor atoms. Does that make sense?
Yes.
Okay. So there is a little bit of a downside to this, but we'll talk about that in just a moment. Now let's say that instead of 10 to the 16, because now I've made an electrically neutral, so I don't have an N well, I just have a place that doesn't have any free charge carriers effectively. So I'll need to go beyond that level. So let's say 10 to the 19 donor atoms. So now I have compensation doped because I've gone beyond the level of acceptor atoms to make that region have an excess of free electrons available for conduction. Okay, that's what compensation or counter-doping is. So if there's a certain concentration of one type of charge carrier, we have to exceed that in order to flip the region to the other type. All right, so now let's talk about what this does. And let me go to my next page. So the counter-doping process does what's called degrading. Substrate. Does anybody have any ideas why it might be considered degraded?
I feel like you get a lot of inconsistencies with the electrical mechanics of it because it's not very homogeneous. Is that correct?
It's actually pretty close. So one of the big issues there is that the doping process is creating ions of a different element with an attached charge carrier. So when we had the example a moment ago when we had an acceptor concentration of 5 times 10 to the 16 and a donor concentration of 5 times 10 to the 16 as well, what that meant was that there was a region of material in our substrate that was electrically neutral, which is what we wanted, but was completely devoid of charge carriers as well, which means that region is utterly useless, right? So all it's really going to do is increase scattering rates, which is going to slow down our electron and hole mobilities as they try to pass through that area. There's a whole bunch of extra atoms there that aren't contributing any free charge carriers. They're literally just getting in the way of the free charge carriers that we have from our substrate doping, right? Outside of our neutral region. So say that electron hole pair recombination. Whoa, what happened? Computer. I need to get one of those stupid gloves where that's like electrically neutral so that I can touch my screen with my hand and it not freak out. Charge carriers. H, not an N, to be clear. Alrighty. So one way to remediate these excessive doping effects is to use a multi-well process. All right, so in a multi-well process, we have a very lightly doped substrate that could be either P or N, and we employ multiple wells. So this guy could be an N well, and this guy could be a P well. And so in the N well, our P plus regions, and in our P well, we'd have our N plus regions, and then our oxide, and have our poly. So one downside to this is that it's going to have significantly more processing steps because we can't create an N well and a P well simultaneously. But the upside is that since the electron and hole mobility is proportional to the sum of the donor and the acceptor ions, using a lightly doped substrate means that we don't have to compensation dope as much. So let me write that down for you guys. Since U, E, and UH are proportional,
Dr. Hartman,
yes.
if you're doing it this way, why would you have to dope it at all? The substrate.
I don't know that you can buy a silicon wafer that isn't doped, to be honest. Like that is a good observation. You could just start out with an entirely different, like an intrinsic silicon wafer. Actually, I'm sure you can buy intrinsic silicon wafers now. I think I've bought some. But one of the reasons that you are going to want to have the substrate doped to some extent is because, like right now, we're looking at our transistors as 3 terminal devices, right? So we have source and drain, which are going to be our P plus or N plus implants, depending on which transistor we're looking at. And then we have our gates, which are our polysilicon. But there's also a 4th terminal on a transistor that's the body terminal. And to create our body terminal, we need our substrate to be slightly doped. Otherwise, we're not going to actually have a good contact. We're going to create what are called Schottky diodes everywhere we try to connect to electrically connect to our substrate. Because we want our substrate usually to be grounded. And if our substrate isn't conductive, we are going to effectively be unable to properly ground the substrate. Does that make any sense to you?
I think so.
Okay. Alrighty. So we've talked about how wells are used in the creation of transistors. Now let's talk about another very common use. And we're going to talk about specifically N-well resistors, although we could make a P-well resistor. No problem with that whatsoever. But we're talking about N-well resistors because pretty much from here on out, we're going to be assuming that our substrate is doped p-type. So in addition to being used to form the body of PMOS. Oh, you stupid computer. Create resistors in CMOS integrated circuits. All right, so hopefully you guys all remember this equation that I'm about to drop on you. We know that the resistance R is equal to rho E, which is the electrical resistivity, multiplied by the length of a piece of material divided by the cross-sectional area of a piece of material. And we can further refine this as rho E times L divided by T, the thickness, times W, the width. And I can draw a little picture here to explain what's what. I'm not giving myself enough room. So this is our thickness T. This dimension is our length. Consider this dimension our width. And so the cross-sectional area, which I'm labeling here as A, is just the face of this rectangular block, okay? Where we're under the assumption that current is going into the front face, like so, and exiting the back face, like so. All right, so in semiconductor processing, all of the N wells will have the same thickness. The designer can only control W and L. So does anybody know why all of the wells have the exact same thickness?
Is it it's the what's the standard, right? The CMOS 5 or what, right?
Yes and no. So the reason why all the wells are going to have the same thickness is during the processing stage, right? There's a beam that is shown down onto the substrate. And that beam has a particular intensity, where intensity is simply the amount of energy per unit area. So if the beam has a constant intensity, then that means that the energy of the ions that are being implanted is the same. So as long as that beam has a constant intensity, you should see that the penetration depth of the ions will all be equal, meaning they can't go any further than their energy allows them to penetrate into the substrate. So that's why all the thicknesses are going to be the same for all of the N wells. And if there was a P well process as well, all of the thicknesses would be the same there too. Because all of these wells are created in parallel in a single processing step. You don't focus a very, very small beam onto, you know, an area that's maybe a square micron or so. You shine your irradiation beam over the whole surface of the wafer all at one time so that all of your wells are created simultaneously, or all of your P wells are created simultaneously and all of your N wells are created simultaneously. So it's a function of the energy of the beam. Okay, so we can adapt our equation slightly. Over W, and we're going to define the quantity rho E over T, since both of those are constant, to be a single value, which we're going to call R square. And R square is what's more commonly known as the sheet resistance. And it has units of ohms per square. How many of you have ever heard of the sheet resistance of a material?
I think we briefly covered it in 336, and we've been talking about it in the microfab class as well, a little bit.
All right, so cool deal. So you guys at least have some, like a little bit of knowledge about it. So the sheet resistance is something that's often used when dealing with, say, thin films and things like that. You know, regions where the length and or the width is typically on a much larger scale than the thickness. Now the units, ohms per square, might seem a little confusing because you may be asking yourself, well, square centimeter, square micrometer, square nanometer. No, it literally means each square, regardless of the dimensions of the square, meaning it could be a 1 meter by 1 meter section or a 1 nanometer by 1 nanometer section, is going to have the exact same resistance. Okay, so that may seem counterintuitive, but that's actually how it works. So from here on out, we're going to be looking at our resistors, not really as a lumped parameter thing like we've been doing in most of our classes, but a distributed parameter. So to determine the resistance of a particular thing, we're going to say, well, we know that it has this much resistance per square, so we need to count the number of squares, and that gives us our overall resistance. And we'll see that in just a couple of minutes in an example problem. All right, so our sheet resistance is dependent on the process node, meaning it's part of, it's determined by the manufacturing process, and we don't really, as designers, have any say within that particular process node to change the sheet resistance. The sheet resistance is also dependent on the resistivity of the material, which means it changes from a particular run of wafers to another run of wafers, right? Because there's no way to guarantee that the exact same number of, say, electrons or holes are going to be created. So it's all statistics, just like everything was back in 334. So typically speaking, the manufacturers or the foundry will do a couple of test feature runs on wafers just to see what the particular parameters are for, say, the sheet resistance and the capacitance between different regions. So poly 2 to poly 1, metal 3 to metal 2, metal 2 to metal 1, metal 1 to the substrate, all kinds of things like that, because those vary literally every manufacturing run. So we can try to kind of best guess as to what it's going to be based on published data, but we have to be able to design to accept small variations in tolerance, because there's small variations in tolerance in the way that wafers are created using the Chojrowski method. All right, so now let's work an example. So I guess I can just do it on the next page since I'm running out of space here. All right. So we want to design a 10 kilo ohm resistor for the C5 process nodes. Where our scaling factor is 300 nanometers, as a reminder. What are the minimum and maximum resistance values for the fabricated resistor? Due to process shifts. And we can say that R square for this process is 0.8 kiloohms plus or minus 20%. So what we're going to need to do is figure out effectively what length to width ratio is going to give us the proper value. So how might we go about doing that? Anybody got any ideas?
Use the equation and adjust. Use the equation. No, but
No, I mean that's literally exactly right. The equation that we have up here isn't particularly difficult, right? We know what R is supposed to be. We know what R square is. So really, we just need to algebraically rearrange and solve for the quantity L over W, right? So if R is equal to R squared times L over W, that means that 10 kiloohms is equal to 800 ohms times L over W, and we can solve that guy pretty easily. So 10 kilo ohms divided by 800 gives us an L over W of 12.5. So any size that has that ratio, the length is 12.5 times longer than the width, will work. There's a couple of things though that we need to look at if we want to see what the physical dimensions of the smallest possible resistor we could make is, okay? So let's look really quick at our design rules. So we are using the CMOS or SCMOS submicron rules. And so the minimum well width is 12 lambda in this case, okay? So all of these rules are scalable. There's actually only one rule in this entire document that isn't scalable, and it's the size of the bonding pads to be able to, for your chip to receive external signals. And we'll talk about that specifically, I think in the next class period. So the minimum width is 12 lambda, right? Since we're only concerning ourselves with one, oh, sorry, this jumped to a bunch of other stuff. This isn't even really what I'm looking for. This is the good stuff. And the reason why I say this is the good stuff is because it also includes pictures that are helpful with applying the rules. So the minimum width is 12. The minimum spacing between wells at different potentials is 18 lambda. And so it's this 1.2 right here where the little hand thing is telling you this is what rule 1.2 applied looks like. 1.3 says the minimum spacing between wells at the same potential is only 6, so significantly smaller. We'll talk about why that is shortly. And then the minimum spacing between wells of different types, so an N well versus a P well, they can actually be extraordinarily close to each other. It says 0 lambda, so you can put them effectively, bump them up next to each other. And I think we'll talk about that a bit later too. So the figure of merit that we're looking for this particular problem, if we want to find the actual dimensions, is rule 1.1. So let's jump back over now that we know that the minimum dimension is 12 lambda. Here we go. Dang it, I shared the wrong thing again. This one. All right. So one other thing that we need to take into account is that we can't do, so for instance right now, if we could say that our minimum width is going to be 12 times our scaling factor of 300 nanometers. So 12 times 3 is 3,600 nanometers, which would be 3.6 microns, right? Anybody have any problem with the math there? All right, nobody's saying anything. Well, the issue that we're going to see is that our minimum length for this resistor is going to be 12.5 times 12 times 300 nanometers. But we can't actually make something 12 and a half units, grid units long. It has to be an integer number, where everything that we're defining will be an integer number of grid units. So 12 and a half would be better expressed as 25 over 2. So that means if my stupid thing can write, that doesn't look like 25 at all. And over here, we need a factor of 2. So that becomes, let's see, it was 3.6, so this will be 7.2 microns. And let me find my calculator because, well, let's see, 25 times 12 is 300. So 300 times 300 is 9 with 4 zeros. Nanometers, which would be 90 microns. So that's actually a reasonably large chunk of material to create this one 10 kilo ohm resistor. So we can use N wells, but we'll find out later on that in processes that allow us to create what's called a high res or high resistance polysilicon layer, we'll likely use that instead because we can get much smaller physical dimensions for the same resistance. All right, so now we talk about what the actual resistance will range from if we have a tolerance of plus or minus 20%, which is fairly straightforward. So R min is going to be 0.8 times R. So 0.8 times 10 kilo ohms is 8 kilo ohms, and our maximum is going to be 1 plus 20% or 1.2 times R, which should be 12 kilo ohms. So since there's such a variation in the sheet resistance, you know, there's a 20% tolerance, we can see that even if we're designing for a particular resistance value, it can be appreciably off. That being said, everything's going to be off by roughly the same amount, so it shouldn't actually influence resistor matching and things of that nature. All right. So let's move along. Now we're going to look at some of the design rules, okay? So first question that we're going to attempt to answer is, why is the minimum width of an N well 12 lambda? And this is rule 1.1, right? So the answer to that is that our process engineers at Moses and the different foundries have established that the quality of resist patterning below this threshold does not meet the quality standards of the manufacturing process. Meaning that the 20% margin of error that we see using a 12 lambda as our minimum width becomes appreciably larger if we make our resistors physically smaller than that. So effectively the tolerance just becomes unacceptable. Now let's look at rule, let me check real quick. 1.2. Y is the minimum spacing. Between wells at different potentials lambda. So if we looked at the cross-sectional view of a substrate containing two wells, so let's say that we have one end well here and another end well here. There's going to be a PN junction formed between the end well and the substrate material, which, let me be clear, this is our P sub, right? So what we actually find is that we make, and when we have two wells, we make a parasitic bipolar junction transistor, an NPN BJT. And so we need to space those wells far apart so that it's much, much harder for conduction to occur between, let's see, this would be the collector and the emitter in this case, right? Because if there's a potential difference, we should see that there's an electric field. Let's say that this guy is at V high and this guy is at V low. We're going to have an electric field in this direction, which is going to try to conduct across, I'm trying to remember what the right term, it's not a, maybe it is a channel still in a BJT. It's been a really long time since I've dealt with BJTs. But anyway, increasing that length makes it much, much harder for that parasitic BJT to accidentally turn on and influence the behavior of the system. So the minimum spacing is turning on the parasitic transistor formed between the N wells and the substrate. Alrighty. Okay, now the last well, not the last thing, but pretty close to it. Alrighty, so continuing to talk about resistors. Sometimes, like as we saw on our previous example, the length of this guy would be 90 microns, which may be unacceptable, right? We might not have 90 microns of free space to just run resistors. So when we need larger resistors, are needed, a folded or serpentine topology may be used. And so this is where counting squares and all that kind of stuff is going to be pretty interesting. All right, so let me try to draw on here real quick. Actually, let's just leave it here. So this is an example of a serpentine resistor, and let me try to subdivide this thing using a different color real quick. All right. So based on our design rules, we know that each of these squares is going to be 12. And each of these regions is going to be 6 based on design rule 1.3, right? So what we've done is we've minimized the footprint of a larger resistor. So instead of stretching out to be one really, really long resistor, we've used probably actually more area per se, but we don't have to have nearly as long lengths of free space. So because this particular resistor is 5 units tall, like so, that means we're going to be at 60 lambda this way. And let's see, so we have 1, 2, 3, 4, 5, 6. 6 times 12 is 72. And then we have 6, 6, 6, 6, 1, 2, 3, 4, 5. So in this case, 72 plus 30 is 102 units this way. But we could count the squares and figure out what's going on here, okay? So one thing that we need to mention, though, is that this method minimizes the footprint of really large resistors. However, each corner has a smaller resistance. And the reason for that is that the current distribution shifts. So we could say that our corner is only going to be a roughly 0.6 R squared. So for a C5 process, how could we determine approximate resistance value of the folded resistor? Anybody have any idea?
You sum each of the different, like you sum up the corner resistance, and then the regular sheet resistance, and then the half, like the 0.6 resistance.
All right, so I think I understand what Aiden's saying. So how many non-corner squares are we going to have?
Looks like about 20, maybe.
4 plus 3 plus 3 plus 3 plus 3, so that's like 12 plus 8 is 20. Yeah. How many corners?
10.
1, 2, 3, 5, 6, 7, 8, 9, 10. Yep, 10. Alrighty. And then how many of the small 6 by 12 sections?
5.
1, 2, 3, 4, 5. All right. So the squares, there are 20 squares, so that part's easy. And we know what the resistance to the corner is, so that part's easy. How are we going to do the 6 by 12 bits? If we only know the resistance of a square.
Is it as simple as just half of a square, since it's a 6 by 12? Seems too easy.
So if I cut my rectangles in half like I've done, we can see that it's 2 squares, right? But it's 2 squares in parallel. Does everybody see why that is? Anybody know what I'm talking about?
Yeah, it makes sense.
Yeah, so if we look at this guy, that's a square, and then there's another square down here, and they're connected in parallel electrically because they have this whole node and this whole node shared among them. So from that, we can say that the resistance R folded is going to be 20 times 800 ohms plus, that's our regular squares, plus 10 times 800 ohms times 0.6, which is our corners, plus 5 times 800 ohms times a factor of 1/2. So those are our 5 6x12 sections, where the 6x12 is 2 6x6 squares in parallel. And from this, we can see that we get a 22.8 kilo ohm resistor. So the total area occupied by this guy, let's say that's 60 times 102. 6120 lambda squared. Whereas our previous 10 kilo ohm resistor, so let's see that's 25 length times 12. So this is going to be multiplied by 12, and this is going to be multiplied by 12. All right, so the length and the width are going, these numbers are both going to be multiplied by 12. So 25 times 12 times 2 times 12. 7,200. Right, so just to be clear here. So something like this, right? Yeah. So 25 times 144. All right. Sorry, this should be 25. So 50 times 144. There we go. All right. So we have 7,200 lambda squared, and we get a resistance of 10 kilo ohms down here. We have 102 lambda by 60 lambda, and so we get over double the resistance for slightly less total surface area of our chip being used. So the serpentine pattern has minimized our footprint and actually lowered the amount of area that we need. So that is an interesting result. All right. So let's move along. All righty. So in analog circuits design, their resistor values may be more important than in a digital design circuit. Corners are avoided. By using wires. And these aren't real, I mean, they're wires in as much as they're connecting 2 points in a circuit through a metallic conducting path. But it's not like we're going to throw 22 gauge wire inside of a microchip or anything. So we would actually be using what's called a via, which is a means by which to connect metal 1 to our N-well. Actually, we would be using a via, and a N+ implant, which we'll talk about a little bit later. But effectively, instead of having the corners, we have our rectangular sections like so. And we go to metal 1 and create our serpentine pattern this way. The wires do have some resistance. It's typically much, much smaller than the sheet resistance of the N-well sections. So we do have to take that into account as well. But this is just an alternative way to create a folded or serpentine structure. And what's interesting also about this, the way that I've drawn it with the wire protruding from the top and all that kind of stuff like so, that isn't actually how it would be done at all. So let me just really quickly kind of try to show what it would look like in an actual layout. So you would start with a couple of N-well sections like this. You would put in an N+ implant. And so that N+ implant is so that you don't accidentally create a semiconductor metal junction. So we use an N+ implant because while it is still a semiconductor, it's much more highly conductive than the N-well itself. Then we would put in a via. There's a little plug of tungsten. Now in practice, putting only a single via is typically because if it ever wears out, no longer have complete. And then on top, we would put metal 3. I'm trying to draw, orange is too close in color. Let me do purple for now. Although in extending beyond the N-wells in the top or bottom direction to wire these guys together, it's done higher on the z-axis. Yeah, anyway, sorry, just kind of jumping ahead, but wanted to make sure to explain that you're not increasing the footprint of your resistors by including the wires. All right, so we still got a significant amount of stuff to go over, and I don't know that we're going to get it all today, but that's okay. All right, so I think that's enough about using N-wells as resistors. So now let's talk about parasitic diodes. Stop being a jerk, computer. Stop. Alrighty. So, I don't know why that keeps popping up, but it's starting to piss me off. So, as we discussed previously, when an N well is fabricated in a P substrate. All right, so let me ask you guys a question. I don't know why my computer is just suddenly freaking out, but would you guys care to knock off 30 minutes early so I can try to get this fixed, and then we'll pick up from here on Thursday morning, or do you want me to just keep going?
Whatever works best for you.
Well, I can just tell you that I'm getting incredibly frustrated by something popping up over and over and over again, but I understand that, you know, this is our first real lecture, and so I don't want to bail and piss you guys off, I guess is what I'm saying.
I don't have an issue with it personally, but I don't want to speak for everybody, so.
All right, well, I got 2 votes for sure and however many abstaining votes. Does anybody else care to voice an opinion? All right, well then we will knock off. Oh, let me see what that says. Shit. We can continue from here on Thursday. All right, so let me say that. Yeah, so we'll continue from here on Thursday. I will try to purchase one of those little glove things that are non-conductive so that I can actually stop hitting random weird stuff and try to figure out why this program that I'm using is just popping up random things about changing the size of my pen that I've literally never seen before. I'll put up a homework assignment probably later today. Again, I'm not collecting the homework assignments by any stretch of the imagination. It's just really to kind of keep you in the loop of what my expectation is for you guys to be able to do for your exams and stuff like that. If you want me to look over them, I'm happy to do it. I just want to kind of baby step you through stuff, at least as far as what kind of material might be on the exam, so that you don't freak out and score super poorly like last year's students did. All right, that's enough out of me for today. Thank you guys for showing up and all that kind of jazz, and I will see you Thursday. Thank you.